What's up, everybody? Welcome to lecture 14 over section 2.8. Today's section is all about this idea of what's called related rates. And related rates relies heavily on chain rule. That said, I personally think the easiest way to teach related rates, and most mathematicians, most math educators will agree with this, the easiest way to teach related rates is just by going through examples. Because the thing with related rates isn't so much that there's an algorithmic process that you can follow every time. That's not what related rates are all about. It's more about your approach and your thinking to the problems. One thing that's always helpful when talking about related rates is laying out what the question gives you, what the question is asking you, and based on the question, what you might know about the problem, and then actually drawing the pictures associated with that. So having said that, let's get into this first example here. This first example is looking at the idea of a balloon that's being pumped up. So you're pumping air into a balloon. This is my squeegee thing, my air pump, and I'm blowing up the balloon, right? We're blowing up a balloon so that the volume of the balloon increases at 100 centimeters cubed per second. Now the question is, given that, how fast is the radius of the balloon increasing when the diameter of the balloon is 50 centimeters? Okay, let's break down this question. Let's start first by answering what the question's even asking us. Well, the question is asking us what the rate of increase is in the radius, right? So it's asking us to find dr dt, the derivative of the radius with respect to time. Okay? So the question is, what is dr dt? Now what we're given is that the volume increases at a rate of 100 centimeters cubed per second. That's right here. So that is dv dt is equal to the constant 100. In other words, the derivative of the volume with respect to time is 100. Okay, well, what do we know about this? We know we're working with a spherical balloon. And the volume of a sphere is going to be 4/3 pi r cubed. So we know this. Now, what do we need to do? I'm going to let you all look at this for just a second. Think about it. What is this problem going to need us to do to solve it, to find dr dt? Well, it might help just to draw this picture out, right? So let's do that. Let's draw it out. So we've got our balloon. We're pumping air into it. Let me draw this a little bit better. We've got our balloon. The balloon has some volume, V, equal to 4/3 pi r cubed. And we know that dv dt is equal to 100 cubic centimeters per second. Okay. So this thing is growing. let's take a second to think about what it means to take a derivative of volume with respect to time when there is no time variable in that equation. What is it we're doing? Well, we're assuming that radius is a function of time. So the assumption here is that v is equal to 4/3 times pi times r as a function of time cubed. Okay. Well, this gives us a thought then. Let me erase this here in the middle. This gives us a thought though, because now, if we were to take the derivative of this thing, so this is volume as a function of time, let me write it like that. If we were to take the derivative of this thing with respect to time, d dt of 4/3 times pi, radius as a function of time, cubed, well, we can pull out the constants. So pulling out the constants, we get that this is equal to 4/3 times pi times d dt of radius as a function of time cubed. In chain rule tells us how to handle this thing, right? Chain rule tells us that this has to be equal to 4/3 times pi times 3 times the radius radius as a function of time squared times d dt of radius as a function of time. So the other way we can write this is as 4 times pi times radius as a function of time, that quantity squared, times dr dt. Well, hold up, wait a minute. Wasn't dr dt what we were looking for? Yeah, this value right here, right? And we know that this thing has to all of this has to be equal to 100. So now we have a way of finding out what dr dt is. So erasing all of this over here on the far right. This then tells us that dr dt is equal to 100 divided by 4 pi r as a function of time squared. Okay, well, we've got dr dt as a function with respect to time. How's that going to help us? Well, looking at this, doesn't really matter what t is anymore, because we know what we care about is when the diameter is equal to 50 centimeters. So if the diameter, let's call that capital D, is equal to 50 centimeters, well, that tells us that the radius is equal to 25. So, to answer our question, dr dt, when the radius is equal to 50, is equal to 25, is equal to 100 divided by 4 pi times 25 squared. And now we can go through and reduce all of this. When we do, we get 25 over pi times 25 squared, which is just 1 over pi times 25. And that's it. That's all it is. Just working it out. Starting with what you know, what you're given, and what you're trying to find out. Maybe drawing a picture to help you kind of see the problem a little bit. And then playing with what you know and seeing how you can work out the question. So having said that, let's look at another problem really quick. So in the second question, we've got a few things going on, and instead of writing the question out, I thought I'd just draw it out. So what the question is given that you have a ladder of 10 feet long, a ladder that is 10 feet long, given that you have this ladder and it's resting up against a wall, and that the rate at which the bottom of the ladder moves away from the corner of the wall on the floor is 4 feet per second, how fast is the top of the ladder moving down when the bottom of the ladder is 6 feet away from the wall? All right, so what exactly did I just say? Well, we're told that the distance from the bottom of the ladder to the wall is 6 feet. We're given that the length of the ladder is 10 feet, and that the rate at which the bottom of the ladder moves away from the wall is 4 feet. In other words, dx dt is 4 feet per second. I should have said 4 feet per second, not 4 feet. Sorry. So the question then is, what's dy dt when x is equal to 6? So at what rate is the top of the ladder moving down when the bottom of the ladder is 6 feet away from the wall? We're given that dx dt, the rate at which the bottom of the ladder is moving away from the wall, is 4 feet per second. And we know that if you were to take the length of that ladder and square it, it would be equal to x squared plus y squared. That's just Pythagorean theorem, right? So how are we going to use all of this to solve this problem? Well, one thing we could do is assume that x and y are functions with respect to time. So we can start with this assumption, that 10 squared is equal to x as a function of time squared plus y as a function of time squared. And if that's the case, then applying the chain rule to all of this and using implicit differentiation, we're going to get that 0 is equal to 2 times x as a function of time times dx dt plus 2 times y as a function of time times dy dt. Okay, Well, we know that x is going to be equal to 6, because we don't really care what the time is. We just care when the leg is 6 feet away, right? When the bottom of the ladder is 6 feet away. Time doesn't matter here, really. Okay. Well, if that's the case, then we can also find y. Not just that, we're given what dx dt is. So literally in this problem, the only thing we don't know is what dy dt is. And the way to see that is by working some of this algebra out. So coming back over to this, we're assuming that x and y, like I said, are functions of time. That's why it's x of t and y of t over there. But moreover, we know that 10 squared minus x squared, the square root of all of that, is equal to y. So this gives us a way of translating this information to get this value, this y value. So we have this, we have that, we can get this, and this is what we're looking for. So, plugging all of this together then, coming back over here just to work with this, we know that 10 squared minus 6 squared, the square root of all of that is equal to y. Well, this is going to be 100 minus 36, which is equal to the square root of 64, or 8. So this information right here, this x equal to 6, tells us then that y is equal to 8. Okay? So now we can start putting all of this together and start rearranging things. Reorganizing this down here at the bottom, we're going to get that negative 2x dx dt. Let me move this down a little bit so that sign's not in the way. So we have negative 2x dx dt is equal to 2y dy dt. Well, notice we can get rid of the 2's, and we can divide both sides by y to give us that x times dx dt divided by y, my mistake, negative x times dx dt divided by y is equal to dy dt. Right? So from here, we now know what x is, we're given what dx dt is, and what y is, and we know what y is. So, all of this says that dy dt at x equal to 6 is equal to negative 6 times dx dt is 4 divided by y, we just said was equal to 8. From here, we could do all the algebra to find that dy dt is equal to 3, I believe. You can check, or negative 3, I mean. You can double check my work, but that is how we would go about it. Now it's just a matter of reducing that fraction, right? So again, this process comes down to starting off with the question, what you're given, and what you know. Drawing out pictures oftentimes will help just to visualize the problem so that you can better understand what's going on. Then from there, using what you know to get to an expression that can be populated with what you're given. So we're given that dx dt is equal to 4, and based on the question, we know x is equal to 6 and y is equal to 8. Then using that derivation that we found from what we know to fill in all the unknown data and solve for our unknown. And that's it. That's really the idea of this. I do want to make a point really quick here. Notice this negative value here. This negative value is telling you that the top is decreasing. It's moving down, right? Which is what you would expect. So whether or not a derivative is positive or negative gives you some sense of direction as well. And for that reason, the setup of the problem is important. You need to make sure that all of your signs are in agreement in some way, shape, or form. On an exam, generally speaking, I'm not going to be overly nitpicky about a negative like that. Generally speaking, I'm going to have to see your setup to make sure it agrees, right? If that negative or that positive, the sign, agrees with your setup, all right, cool. However, if it doesn't, well, that's where you're going to miss a point or two, right? Having said all of that, given that we're getting closer to the midterm, I thought right now would be a good time to explain a little bit of how I grade exams. So usually, the way this works, the way my exams work, is every question is worth 4 points. Now, some questions may have multiple parts. I may ask you to derive the derivative of, or to find the derivative of some function. And you might be given 2 functions. That whole question will be worth 4 points, and each individual derivative will be worth 2. Beyond that, if it's just a question like what we just solved here on the board, this thing's going to be worth 4 points. And to that end, I do give partial credit, but I only get half partial credit. So if you're half right, okay, cool, you're half right, you get half partial credit. What I'm going to say is, let's say your setup doesn't agree with your sign. So for whatever reason, you wrote everything out, and you got the sign wrong. Well, you're going to miss 2 points. But you get everything else right, and that's what's important. That's really what I care about. That's why, yeah, I know that sounds like a lot of points for a negative sign, like half the points, but the setup is just as important as the solution itself. Many of you are going to be engineers, physicists, chemists, biologists. Some of you might be mathematicians, computer scientists, etc. The setup to your problems are super important. For example, we all just got through COVID. The math modeling behind that is all calc. It's all calculus. And at that, it's differential equations, some of which you might actually be able to solve after this class. But if you set that problem up wrong, your model is going to be wrong, and if you work for the CDC, you're going to give out some bad information. So the setup is important. I cannot stress that enough. Setup of a problem is as important as the solution to a problem, and both of those together are as important as the integrity you have when working on this stuff. So that is why I take such a strong position against things like cheating, but also why I care about the setup and why I care about the final solution. Having said that, let's look at another problem. Before I move on to this problem, I want to point out I just skipped over 2 examples out of the notes. One of those 2 examples, I like to use in exams a lot. If you could get hold of any of my past students, they will tell you that one of those 2 problems, I used on both the exam 2 or 3, and on the final. So it would behoove you to go back and look through those notes and find out what that problem is. That said, turning our attention now to this problem, again, did not write out the problem. I was not about to draw that out. I am not Da Vinci or anybody else when it comes to art. But I did kind of sketch it out a little bit, right? So what is this problem asking us? This problem is asking, or it is posed as, a man walks along a straight line, or as along a straight path, at a speed of 4 feet per second. A spotlight is located on the ground 20 feet from the path and is kept focused on the man. The question is asking, at what rate is the spotlight rotating when the man is 15 feet from the point on the path closest to the light? Okay, check out the picture because it'll help you connect what I just said to my drawing on the board. But just to kind of give you a rough idea, so the man is walking along this path down here. The point closest to the light, that would represent this vertex up here, is 20 feet away. So the point along this path closest to this vertex, so this bottom corner here, is 20 feet away. And the man is walking along this path at 4 feet per second. Now, I went ahead and drew out a little bit of extra stuff here. And the reason why is because we're going to need it in a few seconds. But to start off with, just looking at our picture, what we want to know is the rate at which the light up here is rotating. So we need to know the angle per second, right? The change in angle per second. And the path is that the guy is walking is along here. And then this leg, the hypotenuse, just represents the path of the light. So the beam itself, right? Now what the question is asking is, what is d theta dt? So the change in this top angle with respect to time, given that x is equal to 15. Now, what we know, or rather what we're given, is that dx dt is equal to 4 feet per second, and that x is equal to 15 feet. And what we know is that the tangent of this angle is equal to something in particular, right? So, using SOHCAHTOA, we have opposite over adjacent. So x over 20 is equal to the tangent of theta. And now from here, we could think of x as a function of time and theta as a function of time, and rewrite everything to solve specifically for x of t. So what I am saying is we can start off with the understanding that tangent of theta of t, so theta is a function of time, is equal to x of t, so x is a function of time, divided by 20, rearranging everything, we get that x of t is equal to 20 times tangent of theta of t. Okay, how does that help us though? Well, it helps us by recognizing that we're given dx dt. So taking the derivative of this whole thing is going to give us dx dt is equal to, the derivative of all of this is going to be 20 times secant squared times the derivative of theta with respect to time. So writing that out, we get 20 times the secant squared of, I'm just going to write theta, times d theta dt. I'll be damned. Isn't d theta dt what we were looking for? Yeah, right? So now, just rearranging all of this tells us that dx dt divided by 20 times secant squared of theta is equal to d theta dt. But hey, we can rewrite this to be a little bit cleaner. Instead of writing 1 over secant squared, or in other words, instead of having secant squared in the denominator, we could rewrite this as d theta dt is equal to dx dt times cosine squared of theta, all divided by 20. Okay. What? How does that help? Like, we don't know what cosine of theta is, let alone what cosine squared of theta is. But we do. Let's look back at what I wrote over here. Coming back to that hypotenuse, we know the length of the hypotenuse is equal to 20 over cosine of theta. But we also know that it has to be equal to 20 squared plus x squared, all raised to the 1/2. And we know that x is equal to 15, so we can rewrite this. This stuff tells us then that cosine of theta is equal to 20 over L, but hey, 20 over L is just equal to, writing it out, let me move some stuff around a little bit, make some more room. So that is cosine of theta over L. This is equal to 20 divided by 20 squared, the quantity 20 squared, plus x squared, all raised to the 1/2 power. So we do know what cosine of theta is. And we do know what dx dt is. So all we have to do now is plug all of this together. And when we do that, we get that, well, we know dx dt is equal to 4. We know that cosine is equal to 20 divided by the quantity 20 squared plus x, but x is 15. So 15 squared, all of that to the 1/2 power, and all of that squared divided by 20. And after some reductions, we can solve the rest of this. The rest of this is just algebra. And that's all there is to it. I know that seems like a lot, but I promise it's really not that bad. Do a couple of these on your own, and you'll get the hang of it. You will see how these work out. It's just going to take doing a handful of them on your own. But having said that, I think this is a good place to stop, so I will leave y'all to it for the rest of the day, and see y'all in the next lecture. Have a good one, everybody. One last thing, I forgot the square up here. Now I'll leave y'all to it. Sorry, everybody. Have a good one.